knock yourself out.
Flavio's going to leave with blonde hair.
Literally.
I'll link it.
Okay, let me
Claudio
catch my breath for a
electrified.
second. Welcome to my session, The Sound of Server, also known as poking the demo gods in the eyes. I hope everything will work. I think it's connected up the way it's supposed to be. And yeah, let's dive right into it. What I'm trying to do here, first of all, is simply listen to how my servers are doing in a different way than just looking at the graphs like we're always doing. Get a different kind of feedback. So I decided to go the easy way and use this. And hook this up to performance counters and stuff.
How does the complicated way look like?
Good questions get a giveaway.
Whoa!
Earplugs.
What is that?
Okay, you got them there.
That does not go into my ear.
It's a plug, definitely.
Yeah,
There's only one.
You want to give away some questions?
but Atos only had 3 pairs of earplugs, so make it good questions. So, yeah, I guess most people here should know what performance monitoring is. I guess you don't know what this stuff is. So here's a picture of the stuff we will actually be using today, the modules. Modular synthesizers are basically mix and match whatever you want to make your own sound. That's really it in a nutshell. You can buy modules to do various functions that the synthesizer normally has, but because you can choose your own modules, you can make it as complicated or easy as you like, any kind of sound you like. You have the weirdest modules. You have modules that simply make a sound. You have modules that will manipulate the sound with filters, echoes, strange wavefolding stuff, which I'll spare you the details of. And I've fallen into this hobby, and first off I could say, if you like wasting a lot of time, want to end a relationship with your partner, because of all cables lying around the place, and you have more money than sense, then this might be very good for you. In general, I don't recommend it, but it is fun. So what we're looking at here is actually what I'm going to be using. So do we have a pointer? I have no idea.
Now show it with the finger.
Easy enough. That's an oscillator. This one's going to be doing my CPU. That's an oscillator. An oscillator just makes a sound, right? That's all it does. You put a voltage in, it produces a sound at a certain pitch. That one's going to be doing memory, if I'm not mistaken. This oscillator here is going to be doing the hard disk usage. I've got some modules here I'll talk about later. I've got a filter here, 2 filters in fact, to tame the sound a bit, because an oscillator by itself sounds kind of crappy and harsh. I don't want to hurt your ears too much. And there's an output module envelope. I'll explain that one later as well. So what I've been doing is finding a way to get the stuff from the computer onto this. Quite a search. And of course, with all the searching, I forgot to actually take a screenshot of the device, but it is built into this box here. It's a small industrial device for measurement computing. What I need is analog voltages. This all works on analog. There's a simple standard for these synthesizers. If you're going to be working with pitches, 1 volt is 1 octave increase. What I need for this, so for the pitches, you have, it's 1 to 8 volts. You can go up 8 octaves in general with the standard. That's already really high. I've limited it for this demo that it doesn't go up too high. But basically, it's just the amount of voltage you put in there, that's how high the frequency is of the sound that comes out. Really in a nutshell. You also have other kinds of signals, control voltages, which are for manipulating the sounds. So I can say, well, I want more filter or less filter with any voltage between -10 and +10. And you also have triggers and gates, which are 5 volt logic, which is great because that's an industry standard. And that worked fine with my I/O box. Finding an I/O box for this is actually not that easy. Everybody's doing digital, of course, for some reason, losers. So you can easily get a 32-channel I/O box for next to nothing. This is 8 channels of 16-bit volt out, and you can't use a sound card for that because the sound card doesn't have direct current. This thing can do that, and this was actually more expensive than many 32 or 48-channel digital boxes I found, but it requires a bit more technology and not many people use it. So I took that, built it in here, so I have my mini jacks that I can use to plug everything through, and that was basically how I get the stuff from the computer to the synthesizer, with a lot of code, which I'll attempt to demonstrate now. So what I've been doing is actually kind of fun. It's using reflection with .NET. Many devices, the better stuff just comes with .NET DLLs. You can load it into PowerShell using reflection, and all the functions are available straight away. And if you have good documentation, you can simply take the C calls and translate into the data type for PowerShell, and it's it just works by itself. I'm not a programmer at all. I've been learning a lot on this project. And it's really easy. I encourage anybody, if you have a .NET DLL, you want to do something with a program that uses .NET, try loading the DLL up. IntelliSense will fill it up for you, and you can just see what functions are in there and research from there on. So that's basically what I'm doing. Just loading a reflection of this DLL, creating a new board, and if I run this, yep, it's actually working. That's always good news. So now I have an MCC DAC object, and I have an MCC DAC board. I need to click in the right place. Did I just destroy something? Okay. That's it. It's as easy as that to get .NET into PowerShell if you want to use it. And then you start basically translating the calls that you want to PowerShell modules. That, I could have done C, but I'm not familiar with it, so I painstakingly changed all them and made them into the more standard modules. I'll show in a minute. About this code, this code here is more or less just controlling the board. It hasn't got anything to do with the synthesizer yet. There's no translation going on here. So what I'm doing, I've loaded up the board. I've made a new board object. For further on the presentation, I need to make a buffer from which I can load values into the box. That's a special buffer that the DLL has for itself. So here I'm allocating 8 bytes to that buffer, or actually 8 byte pairs, if I'm not mistaken. It's 8 byte pairs into the buffer, which I can load later. Because I'm loading that all the time, I'm declaring that here already because I'm reusing that. And for example, here we have one of the simple codes. I just want to set the pin output with a 16-bit value. So I pass a pin and the value onto it, and this is all I need to do, this small piece of code here. Can people read this, by the way?
No.
No.
Okay, that's a good point. Somebody could have mentioned that.
Can't read it.
Now I know.
Thanks.
Yeah, let the synthesizer read your code. Okay.
It's, where's Gunnar? How fast can you implement that? So, yeah, just passing some parameters, and it's a simple call. And all I'm doing is saying the pin. The second value is a range value, but with my cheapo board, the range value can't be used. I need to set the range inside the application. Which in fact, I'll quickly show you because, of course, I forgot to check something with that. Sometimes it resets certain settings, so. But yeah, really simple stuff and fun to do. Yeah, it's setting slave mode, okay, all good. And this way I just started taking calls from the documentation and slowly putting them in here. There's actually a lot of stuff in here which this board doesn't use, but I figured I might want to get a bigger board in the future, so I just put that in there. So it's got several calls. You can use a 16-bit value, or I can just directly say what voltage I want the pin to have. The analog pin scan output, this is actually a nice function. With this I can load 8 values at the same time and also tell it to delay till there's an external signal to sync everything at the same time, because you don't want the signals changing step by step. That's a bit not very useful for music. Even though it's probably so fast you wouldn't hear it, but it becomes useful later on. Lots of parameters, all of which I've done nothing with. I've just put them in here because I'm anal, but the board doesn't actually do anything with these. Something to do with the simultaneous mode that has to do with the loading of all the codes at the same time. So yeah, I can go through all the functions, but I think you guys get the idea. But it's a really good moment when you're doing this. I had no idea what I was doing. I knew reflection existed, but then I got the first LED to flash. There's like a test function, flash LED, and that was brilliant. I've got something working, and then you know you're going to be okay. And I thought of doing this really nicely. This is something I quickly want to show, even though it didn't work out for me, but it is very cool. And that's making classes in PowerShell 5.1. Well, forgot to remove some old code. Which was really nice. I can make an object which is completely reflects the actual board. So I can just do the standard stuff, get MCC DAC board, A pin, will tell me the voltage. If I say A pin 1 is this net, it will set the voltage. All kinds of functions going on underwater, but it turned out I couldn't actually load reflection inside this. And I didn't have the time to rewrite the whole thing. So I had my class ready, all my calls ready, and then I couldn't marry the two, but it's something fun to look into if you like programming. Making classes inside PowerShell can go really far. So I reverted to just using simple functions. And I'll just load this one up. So actually at the top here, I'm dot referencing my MCDAC. And now I'm ready to play notes on this if I want. Before I do that, I'll quickly switch something on here. So let's have a look. I've got it set up for a sequencer now, so you can see a bit what it does, but it's not outputting arbitrary values from CPUs. Problem right now is that the frequency is really low. It's not actually hearing anything. But this is just arbitrary stuff. This is called a Turing machine. It's a bit shifter, and every bit has a certain value, and these values get added up together. You can manipulate all this stuff. A lot of the music people make with this is actually random stuff, and at some point, if you like it, you hold on to it and you start playing around with it. Etc. So that's the basic idea, and I need to rewire something quickly for this.
Make a Zen server sound.
Make a Zen server sound.
That's it. That's a good one.
1 second while I plug some cables. Let's have a look. So
Claudio, when you hear that, Zen server is the first that comes to your mind?
When I go to the
That's the point. So where's my voltage? In here.
Rare synesthesia between hypervisors and sound.
Yeah, we can hear the difference between hypervisors. I want to see that now.
Oh,
Right.
Let's see the
Sorry, get the mic back. So what I've done here is simply started translating musical stuff to calls I can make with the MCC DAC modules I have. For example, up here I have cool. Right, everybody dizzy already? This simply translate, with this I can play a note and have it translated to a 16-bit value to be really exact. For that I'm using the enum table, which is really nice. It's simply a big lookup table, but what's good about this is I can get very accurate. I've no idea, zero should be 0. I can get really accurate values instead of just using the standard volt, which can be off a bit. These oscillators, this is analog stuff, right? So it will drift, they will not always be in tune properly. So in fact, in the future, what I can start doing is making different enums for each module and just get exactly the right tuning, which is not really possible inside the analog world itself. So I could theoretically do that with this. It's just a big list of notes. So F4 is going to be 28,944.625, and FS, that's F sharp. I was going to put the official hash symbol in there, but I couldn't get it to parse, so somewhere I need a literal string translation because I couldn't figure it out. I figured I'll take the easy way out. So that function just translates it to that. Here's a function for setting the tuning. I can set all the oscillators to the same note at the same time. And here's a function for playing notes. And with this, I can send an array of notes in here, which is simply I tell them what pin I want to play, what note, and the note is actually an array value as well, with the length of the note, with the pitch of the note and the length. So I've got a small example here, which is literally random, so this should work. Where the hell is it? In the dark. Rock and roll, we have sound. So that's a start anyway.
The official song of
But now what I need to do is start monitoring the performance of the actual machine, and that's, PowerShell is like the worst choice you can make for this kind of stuff, but it's the only thing I know. But normally there's, unless you start doing more complicated stuff, there is no multi-threading. And if you want to get an average performance counter, oh god,
The
I need that.
organizers tell me I need beer.
Thank you. If you want to get an average of a performance counter, it takes a second. Now, I'm not pretending I'm going to be making great music with this, but anything musical, I need updates more often than once a second. So I tried various ways. One way you will find on the internet, which I'll immediately advise against doing, is this method, which simply takes single samples and takes an average. So this way you can say, look, I just want 10 samples, that's going to take me like 20 milliseconds, that should be fine. It doesn't work. You get way, way higher readings than you're supposed to get. My suspicion is, because every time it's pulling the CPU, if you get an average sample, it will pull all the different cores. But because this time I'm starting sampling all the time, all over, I noticed that my core 1 was spiking. It was actually giving the numbers of core 1, but they were way too high and it was bothersome and not working properly. So, run spaces, very nice. I was happy to discover this. A way to run multiple processes at the same time with very little overhead inside PowerShell. I'm not going to go into the details of how this works because I don't really know. I'll just say already, in case I forget later, I need to thank everybody on the internet ever who wrote the word PowerShell, because I'm sure I've been on their site in the last few weeks. But in a nutshell, I'm creating 12 processes, so I want an update about every 100 milliseconds. Then I know even if I'm going really fast, I can have, if I'm playing 10 notes a minute, 10 notes a second, I can have different pitches for each note already. So what I need to do is have this running in the background and at some point gather the data. But I want it every 100 milliseconds, so if I repeat it, that's not going to work. So I have actually 12 of these running in the background, each with a 100 millisecond delay between them. And they are writing to a variable which is shared between these 12 run spaces. So every time it's run, it will start a sleep, which is the new time span from, so it's the difference between the start date, the current time and the start time. So when I launch all these run spaces, I simply say, look, I get the date right now, add 100 milliseconds for each one, and they have that in there, and every time it loops around, it adds another 1200 milliseconds. So it will it'll keep more or less the same distance from each other, you could say. These are overlapping processes, and they will sleep till things are done.
This is the best while condition I ever saw.
Yeah, I'm sure there's a cleaner way to get like a process to run continuously.
I didn't even notice that.
You should have just done both, but yeah, let's go with L equal frozen over.
Yeah. I knew there was something better. I was like, it was late. I was tired. Okay, Jim.
No, that's going in my code from now on.
You have to wrap everything with it, just in case.
So this is basically the script block that I'm going to run. So processor time, logical disk this time, and then memory committed bytes. It's all percentages, so it's nice and easy to work with, instead of getting all kinds of different numbers. Here it starts, and for each process it's going to add, every time it runs, it's going to add these 1200 milliseconds, and just get the counters and put them in sync hash. So what will happen sometimes if it's just running along, and I'm retrieving the values from sync hash all the time, because my front-end process is not synchronized with the back-end. Once in a while you get an error, like, while we were retrieving it, the sync hash was updated. But that doesn't matter, I put a catch in there, and then you just get the next value. And because it's going so fast, it doesn't make much of a difference anyway. This is the actual creation of the synchronized table, getting the date. Say what the start times are, it's an empty array, and going to fill it with objects. So for each one I add another 100 milliseconds, so it becomes 1200 apart. And this is the part I'm not quite sure how it works. So these ones I know, and this one here, like, yeah. Okay, so I'm creating a run space factory, putting stuff in there. This here is saying I want a minimum of 1 and a maximum of 12 objects at the same time. It doesn't make much difference in my case because I'm consciously running 12 objects, but if you're using run spaces, let's say you want to have 250 run spaces but only 25 at the same time, this is the place to set that up. Session state is just create a default session state. It needs to know what state it is in when it starts. And it's going to open it, and then for each run space, going to send my arguments that I set up earlier with the start times and everything. I'm sorry if this is a bit confusing and fast, but I realize as I'm going through this that I'm going to so run out of time, so try to get it in here. Basically, start run spaces, and at the end, if I want to get rid of the run spaces, I just kill it. So let's run this function and get those run spaces running. And let's have a look. So these 12 are now running in the background. And this is, this is a nice laptop, but it's kind of old. And you can still see the performance hit I'm getting from this. Meh. It was a small spike when I started it up. In general, it's saying 2% now. When I was running the sampling, I was getting 30% performance on just one CPU. And in general, the whole system was stressing out more, so run space is the way to go for this. It's very little overhead. It's better than running things as a job, because if you run as a job, every time it will load the entire environment. These are just sub-processes. Thank you for your approval, Jim. It's appreciated.
I like run spaces, they're cool shit.
They are, they definitely are. So these are running, and I'm not going to look at them anymore because they just keep on running in the background. And now in my Eurorack, let's close this one up again. I also have a function to start actually monitoring stuff. So here's start Eurorack feedback. What I'm doing is, because I'm using 16-bit values and the exact numbers, yeah, I can explain all that, but it's not very interesting. Basically, I'm just taking the percentage and multiplying it by a certain number, so I know I stay within octave range using that 16-bit value. If I were to send the maximum 16-bit value, my oscillator would get 10 volts, your ears would be bleeding, and probably this would be smoking because that's out of spec for it. So I'm keeping it to about 3.5 volts, so the octaves are not jumping around too much. And it's going to get these from the sync hash array. It will write what's happening, and then it's actually going to set the analog pin scan output, so all fields at the same time with the counters I have. So let's have a look. And again, well, hell is now it's frozen over. And let's have a look here. And here I'm doing something, I'm setting one of the digital pins, but I'll explain what that's for in a minute. So let's run it. Let's have a look. What's our function in? Crap. So what you're seeing now in the left column is the raw numbers, the raw int16 numbers from the CPU. On the right, that should be hard disk activity, and the middle is 0 is the committed bytes. That's not that much, unless I'm getting my things mixed up. No, actually the third one is committed bytes, and the middle is disk, which is not doing much at all at the moment. So let's listen what's going on. Excuse me. Amazing. But you can already see, once I start opening things up, that's the CPU.
That is great.
I always thought, Chrome sounded like that every time I open it.
Oh, yeah.
That's really good.
Chrome is a bit so this is just a CPU we're hearing now, right? And I would like to maybe hear some more sounds as well. So now I have to figure out what I need to turn open on this thing again, because I'm also already outputting the memory in the hard disk activity. So if I'm not mistaken, let's have a look. Always good this. Anybody who's into EDM? This is what your DJ is doing half the time, by the way. So you'll have to generate some hard disk activity. So that's, now I'm monitoring 3 things at the same time. It's not very musical yet, is it though? So yeah, we need to do something about that.
I bet we could.
Yeah,
Get rid of that. Maybe not get rid of that. Okay, whatever. Okay, so I'll just turn this down while I patch a few things. I'm gonna put the microphone down and just shout while I'm doing this because it's a picture with one hand. So what I could have done is program the whole thing. It's going to tie it to certain nodes. I'm going to have a melodic thing as well. Great, but these things think of that. We have a module called a quantizer. Let's just quickly pull that up. So what we're going for now is actually this. Oh, no, this is what we've actually just done, so next one. Yeah. This is a really simple patch, by the way. Anybody wants to learn more about this, Google a guy called Ebotronics, then he makes me look like an amateur. Sorry?
Is this in the manual?
Is this in the manual? No, this is this is what I built myself. There's actually a website you can configure these things completely virtually. It doesn't make the sound, but you can make the patches and stuff, which is useful for things like this. So, want some earplugs?
Bugs.
So let's just see. Oh, well, on my patches I completely forgot to put the quantizer in there, but in a nutshell, no, if a voltage is not tied to a certain node, if it's not tuned properly, it will tie it to a
Use the
node.
mic if you're not using your hands, mate.
Okay. Well, I talk with my hands, dude. But yeah, basically, let's say you're going to have 0.99 volts. That should be a C, more or less. It's a bit more complicated, but it isn't a C, it's going to be out of tune. So I want to quantize that. So the quantizers in here will tie to certain values. These are actually digital components. They just take the analog in and measure it. Say, okay, so the closest node for that is this and this node. So I'll need to repatch for that for a second. Let's have a look. Dum, 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 dum. So this one goes into, where did my quantizer go anyway?
You didn't want it. Oh, it comes today. But only the training maybe you should take a bit Delphin.
That's assessment well.
Next time Dolphin.
All right, all patched up. What I need to do for a minute is stop this. Because I'm actually going to be using proper notes now. This is analog stuff, so every time you use it, you need to tune it. So now all the oscillators are getting the same value. That doesn't sound very in tune, so let's get the tuner out. Great, the tuner's not actually picking it up.
It's when he turns around and roll on the floor. That.
I tried to make a name.
Not sure which oscillator. Okay.
Eventually we hit the frequency that makes us all puke.
Let's bring the second one in again.
I'm really starting to empathize with your neighbour's tongue.
Well, I tried to keep it down at home, but you know.
Who needs neighbours?
right, now it's actually tied to notes. We're starting to get somewhere.
And I understand a bit about losing your wife or girlfriend.
Well, yeah, Sasha and Chris are sleeping in my place. They can attest to this. So let's get some CPU load in there. Let's do some memory this time. So we actually have notes now. But still, this is like, you know, that's okay, but now, you know, if you're going to do anything musical, you want some kind of timing in there, right? So here's the good thing about this card, the fact that you can load all this stuff simultaneously with an external signal. This is just like the normal digital world, 5 volts, like any industrial level machine, so it will speak with this perfectly fine. The reason I was setting the digital pin all the time when I was running my loop was because I had to update this. So I was actually sending a digital signal from my first pin out to my synchronizer, but now I can just take my clock because I have one. Now I actually have a clock running here, which is going to send pulses. Every time this box gets a pulse, it will update the value. So this is completely asynchronous. It's not actually locked in time with this at all. Don't really care. I just want to get some kind of metronome in there. So let's have a look. You don't hear much of a difference. Well, that's because I've still got the volume open all the time. So now we need to start doing something about that. So, for example here, now I've got a low pass gate and an amplifier opening up at the same time. So it's opening up the lower frequencies, opening up the higher frequencies, sorry, and the volume at the same time. It's a West Coast Buchla style thing. I'm sure you've all heard of that, low pass gate. And the thing is, I reconfigured this case for this demo, and I really need to find my modules right now. And here we have an envelope. An envelope is basically creating how fast the sound goes up in volume. I think I may have an update going on or something. Sounds familiar, Gunnar?
He loves to be screaming because he's got Windows Update.
So, what do I need for this? Let's just turn the volume down a bit while I do that. Seriously though, does anybody see my envelope? Yeah. Here is a wire going from the clock to the envelope, and here is an output. Okay. That's a start, that's the mem and hard disk going. And now I just turn this one back up. Eugene, you want to do your thing generating some load? Yeah. So Eugene's going to help me here. I think you might be safer coming through this side. So this is where it all comes together. I've actually got things running in time now. And now I need one more cable.
Where's the synchronizer?
So this is the envelope. Yeah, but we need to switch it back. If anybody's ever going to use heavy load from Jam software, it's kind of funny, but don't use the memory option if it goes your machine. So here you just by saying start somewhere. So Eugene on performance counters, and I'll just hook up the last few things here. So of course we are missing one vital thing here. So I'd say bring on the Vermona. We need drums. That's basically how to do something really stupid.
Just put this
There are-
sequence on YouTube, that's gonna go viral. Best eating presentation ever.
I have an actual question. Yes, sir.
Control up that goes outward,
Well, I do weddings and parties if you're interested.
How does this fit into GDPR?
There are two things I'd like to point out here, though. It's, of course, it's kind of stupid, but it's fun. And there is a thing that we are using visual cues all the time. Well, sound actually we react to way better. We've all had this thing: you get in your car, you're driving, and everything feels fine, but it doesn't sound right. And a few weeks later, something breaks. Or if you go into the server room and it's silent, you know you have an issue then. The sound is a very interesting cue. How the heck you would use that in the workplace apart from just having a siren going off when the server goes down, I have no idea. I don't think this is the best plan. But
Not if you need one of those per laptop, no.
well, I mean,
Well, there's a lot of blind administrators, so.
that's true.
And if you're blind and
Yes.
really rich.
Can you do it virtually on the computer? Like having this machine as a...
Yes, there are VSCs you can use for this. I guess then you would need to write a code to convert to MIDI. They're not really going to accept.
Steinberg Reason, for example.
There's- there-
Analog, right? So you can simulate it, but you'll never get.
The same now.
Yeah, but on the other hand, to be honest, I mean, I really like this stuff because it's got lots of blinky lights, buttons, and may I point out, we can't see any of the lights, but these are glow-in-the-dark cables. Just saying. But the same
lights.
No, we tried, but they can't get enough lights to see anything. Can you still try? Yeah, let's see the cables. Yeah, try it.
Kill the light?
Yeah. But the more important point is actually, I wanted to do more with PowerShell. I really like PowerShell, but I also like some... Mike, oh, sorry. The more important point is I really wanted to do more with PowerShell. I think it's great fun, but I like having some kind of goal. So I just found a goal which is up my alley, and I learned a hell of a lot. I think I wrote probably a couple of thousand lines of codes, and what's left is what you see here. So the rest of all the stuff I learned didn't work, which is very valuable as well. And that's the thinking behind it, really. Just find some use to do something silly with code or whatever you want to work with. Go for it, and well, see what you end up with. And it might actually be this crap. So, yeah, I hope you all enjoyed this.
Yes, very much.